Imagine letting go of a ball. It falls. Now imagine throwing it sideways fast enough that, while it falls, the Earth curves away beneath it. The ball never reaches the ground. It becomes an orbiting satellite. Newton described both motions with a force called gravity. His law works so well that engineers still use it to guide spacecraft. But Einstein asked a deeper question. What if gravity is not, at the most fundamental level, a force pulling objects through space? What if it is the shape of space and time themselves? That is the central idea of general relativity. Matter and energy shape space-time. Curved space-time shapes the natural motion of matter and light. In this video, we will build that idea carefully, see what the famous rubber sheet picture gets right and wrong, and finish with the evidence that turned an audacious theory into our best description of gravity. Start with a problem hidden inside Newton's picture. Suppose you stand on the ground, holding an apple. Gravity pulls the apple downward, yet the apple does not move. The ground pushes upward on it with an equal supporting force. Release the apple and that support disappears. The apple accelerates downward. Our everyday language says the falling apple is the one being forced. An accelerometer says the opposite. Resting on the ground, it measures an upward acceleration because the ground continually prevents it from following its natural path. During free fall, it reads approximately 0. The falling apple feels weightless. So do astronauts in orbit. They are not beyond Earth's gravity, they are falling around Earth. Einstein's decisive clue was the equivalence between gravity and acceleration. Picture a sealed lift far from every planet. If a rocket accelerates the lift upward, a loose object appears to fall toward the floor. A beam of light crossing the lift appears to bend downward, because the lift rises while the light travels. From inside, the effects resemble a uniform gravitational field. Now reverse the thought experiment. Let the lift fall freely near Earth. The occupants, the loose objects, and the lift itself all accelerate together. Locally, gravity seems to disappear. Einstein elevated this observation into the equivalence principle. In a sufficiently small region, the effects of a uniform gravitational field are indistinguishable from the effects of uniform acceleration. The phrase sufficiently small matters. Across a large falling lift, Earth's pull is slightly stronger at the bottom than at the top, and points in slightly different directions from side to side. Those differences are tidal effects. They cannot be removed everywhere by choosing one freely falling frame. Tidal effects are the local signature of spacetime curvature. To see why geometry enters, we need spacetime rather than space alone. An event has both a place and a time. A moving object traces a path through this four-dimensional structure, called a world line. In special relativity, with gravity absent, spacetime is flat. Free objects follow the straightest possible world lines. In general relativity, the geometry can vary from place to place. The mathematical object that records intervals, angles, and causal structure is the metric. Once the metric is known, it determines which paths count as straight. In curved geometry, the straightest possible path is called a geodesic. This is not merely a change in vocabulary. In Newton's account, the Sun exerts a force across space and bends Earth's motion. In Einstein's account, the Sun changes the geometry around it, and Earth follows a geodesic in that curved space-time. An orbit is a kind of free fall. Earth is always falling toward the Sun, while its sideways motion keeps it from colliding with the Sun. Light follows the same rule. A light ray has no rest mass, but it still follows the geometry of spacetime. That is why saying only that mass attracts mass is incomplete. Gravity acts on light because gravity is not simply a force between massive objects. It is the structure through which matter and light move. Here is the familiar rubber sheet analogy. Place a heavy ball on a stretched sheet and the surface dips. Roll a smaller ball past it and the smaller ball curves around the depression. The image communicates one useful idea: the presence of matter changes geometry, and that changed geometry alters possible paths. But the analogy has serious limits. First, the sheet curves into an extra spatial dimension, while real spacetime curvature does not need an external dimension. Curvature can be measured from within a geometry. On a sphere, for example, the angles of a large triangle add to more than 180 degrees. No outside viewpoint is required. Second, the rolling ball on the sheet is driven by Earth's gravity, so using it to explain gravity risks circular reasoning. Third, the sheet represents space, while much of ordinary gravitational motion comes from the curvature of time. Clocks nearer a massive body run more slowly relative to clocks farther away. The full theory curves spacetime, not just a two-dimensional surface. So keep the rubber sheet as a visual metaphor, not a literal mechanism. Einstein compressed the relationship between matter and geometry into a remarkably compact field equation. On the left is the Einstein tensor, which describes spacetime curvature. On the right is the stress-energy tensor, which describes the density and flow of energy and momentum, together with pressure and stress. The constant between them sets the strength of gravity. In words, the distribution of energy and momentum is related to the curvature of spacetime. The equation is local and dynamical. Matter is not the only source. Radiation, pressure, and every form of energy contribute. And the resulting geometry can itself change and propagate. You will often hear the slogan, "Matter tells spacetime how to curve, and spacetime tells matter how to move." It is memorable, though slightly simplified. The field equation determines geometry from stress energy, while the geodesic equation describes free motion in that geometry. Together they form the two pillars of the theory. A good theory must do more than sound elegant. It must make precise predictions. First, Mercury. Newtonian gravity explains almost all of Mercury's orbit, but the point of closest approach to the Sun advances slightly more than Newton's theory predicts. General relativity accounts for the unexplained remainder, about 43 arcseconds per century. Second, the bending of light. Because light follows curved spacetime, a massive body can deflect a passing ray. During the solar eclipse of 1919, observations of stars near the darkened Sun agreed, within the accuracy then available, with Einstein's predicted deflection. Today the same effect, gravitational lensing, lets astronomers map otherwise invisible mass and observe extremely distant galaxies. Third, gravitational time dilation. A clock deeper in a gravitational field ticks more slowly relative to a clock higher up. This is not an illusion of a faulty clock. Different paths through spacetime contain different amounts of elapsed proper time. Modern atomic clocks measure the difference even across small changes in height. Satellite navigation must account for relativity. GPS clocks are affected by both their speed, from special relativity, and their higher position in Earth's gravitational field, from general relativity. Without the corrections, positioning errors would accumulate rapidly. The theory also predicted stranger phenomena. Compress enough matter inside its Schwarzschild radius and an event horizon forms, the boundary of a black hole. Accelerate massive objects asymmetrically and disturbances in spacetime can travel outward as gravitational waves. In 2015, LIGO directly detected such waves from two merging black holes, almost exactly a century after Einstein completed the theory. Even here, precision matters. A black hole is not a cosmic vacuum cleaner, and a gravitational wave is not matter moving through space like air through a room. Both are consequences of spacetime geometry governed by the same field equation. Now return to the falling ball. Newton tells us how to calculate its acceleration with extraordinary accuracy. Einstein reveals why free fall is special. The held ball is forced away from its natural spacetime path by the ground. The released ball follows a geodesic. The orbiting satellite follows another geodesic. Light passing the Sun follows a null geodesic. Different appearances, one geometric principle. General relativity does not say that matter is unreal, or that gravity is merely a drawing on a grid. It is a physical theory expressed through geometry. Its concepts distinguish what an object feels locally from the tidal structure that remains across an extended region. That distinction is the heart of the equivalence principle. So the next time you feel your weight, remember, what you feel is not gravity pulling on you. You feel the ground preventing your free fall. Beneath the ordinary act of standing still lies a curved four-dimensional world, in which planets, light, clocks, and even ripples of geometry obey one coherent order. Gravity is geometry. And geometry moves the universe.